That's fine. No worries. I appreciate you came. That's the important part. Okay. Yeah, we seem to be all set.
Welcome, everyone. I'm Rob Tixerani. David asked me to fill in for him because he's out of town. Happy to have Aleksander Madry of MIT EECS giving our class today on robustness and machine learning. So welcome.
Great. Thank you. Welcome everyone. So it's always fun to be at Stanford. So yeah, what I want to talk about today, actually I was thinking quite a bit about what to talk about today. So I think I look at the previous lectures and they were kind of theory heavy, and I thought, okay, I could either try to do a bit more of theory or more give you the, I would say, bird's eye of the whole field. And that's what I end up doing. So today there will be not too much theory. It will be more about telling you what this robustness is about, what kind of questions we try to understand there and attack, and what's going on. Okay, so let's get started. So I am sure that's not what was supposed to happen. Sorry. That was way too fast. So essentially, I think I don't have to tell you that machine learning is in quite interesting place right now. So indeed, things that we seem to be able now, to effortlessly do now, seem to be just science fiction maybe 5 or 10 years ago. Okay, so that's all very exciting. Actually, quite a lot of people got quite excited. And currently, the feeling is that machine learning should be put into anything that we do. Okay, so whatever you do, if you are not doing machine learning and even better, deep learning there, then you are doing it wrong. Okay, so that seems to be the spirit of of much of what's happening in computer science nowadays and beyond computer science. And this, of course, makes in particular me wonder. Okay, so as cool as the machine learning we currently have is this machine learning actually truly ready for real-world deployment? And there is a couple of questions here. So one question is, do we really understand how, why, and even if this ML toolkit actually works? And I would say it's highly unclear to me. I guess this class shows you that there is quite a lot to understand there. But the other question is that even if the things that we think that work, can we actually truly rely on them? Okay, and this is the kind of question that I want to focus on today. Okay, so can we truly rely on machine learning? So what do I mean by that? So what I don't mean by that is kind of the Elon Musk style Skynet scenario. This is really not, the more I work in machine learning, the less worried I am about the scenario in the near term. Okay, maybe long term it might be different, but that's not something I am worried about in the near term. The things I actually am worried about is that this pattern that we see that whenever we deploy machine learning driven solutions in the high stakes scenarios, well, there are some bad guys who can use that to manipulate this, this fact that we're using machine learning to to undermine our systems. And this is not only the case when there really are actual bad guys trying to undermine our systems. It also happens if we just the bad guy is nature. Essentially, as we deploy things in the context that matter, we see that the reliability and safety is actually a concern as well. Okay? So this motivates this, very broadly this need for, let's call it robust ML. And let's try to make it a bit more concrete of what it is that worries us, or worries me in this context when we talk about robustness. Okay, so the nice point of start here is one of the clearly the home runs of machine learning, of deep learning in particular, is namely the ImageNet challenge. Okay, as you know, it was actually developed here at Stanford. ImageNet challenge is this a computer vision object recognition, object classification challenge, in which we get around 1.3, 1.4 million of high quality images that can be classified into one of 1,000 classes. And then our job is to train a classifier on this, on this data set, and then take a test on the withheld test set and get good performance. So what you see over here is the progress on this challenge over the, since the inception of this data set and this challenge in 2010. And there are two important inflection points over here. So one inflection point is over here. In 2012, this is where the Aleksander paper came out. And as you see, the progress that it made on reducing the error on this challenge, so this is actually a top 5 error. So essentially what happens here is that you ask your model to give you 5 potential predictions, 5 classifications for a given image. And if one of them is right, you are right, otherwise you are wrong. Okay, and this is the fraction of test images that the model still got wrong. So we see that in 2012, the AlexNet really improved over the state of the art by quite a bit, and essentially this was such a shock to the community that after that, all of the computer vision community just switched to deep learning immediately. They realized that this is the way to go. And indeed, over years, they were able to reduce the error more and more and more. In particular, around 2015, they actually got an accuracy that rivals that of a human, or humans, or in particular a human, Andrei Karpathy, who actually trained himself on this, on the ImageNet challenge and took the test, and that's the score that he roughly got. Okay, so on one hand, this looks very impressive and kind of scary that these deep learning models seem to be able to to have better vision than humans. But kind of the reason why I bring up this example is that actually it's a good reminder of sometimes trying to really understand what this kind of successes, which are undeniably successes, really mean. Okay, and kind of what this brings me to is something that I call the biggest lie of supervised machine learning. Namely, this supervised machine learning framework, the one that we usually use to think about, is actually very beautiful and convenient. And roughly, it revolves around this notion that there is this distribution in the sky of all the inputs that we can ever want to classify. Okay, so essentially, we just think that in the sky, whenever we think of an image, there is a distribution of our images that we will be actually, ever wanting to classify, ever want to interact with. And now, the way training happens is that we sample some number of independent samples from the distributions. We train our model, and the way we evaluate it is by just getting some more of the samples from the distribution and seeing, kind of the measure of performance is the fraction of mistakes that we do here. So this is an extremely clean and appealing model, and it drove a lot of, amazing developments in machine learning. But it is, in some ways, inherently wrong, because in reality, on any task that actually matters, it's really it's almost never the case, if actually it's never the case, that the distribution that we train on is the actual distribution we deploy the model on. So somehow the picture to have here is that there is some distribution that we sample from to train our model, but then the distribution that we actually care about performance on might be actually quite drastically different. Okay? And you might say, well, that's how theory works. You make some assumptions that are sometimes unrealistic, but in the end, often things are still okay. So, what can go wrong here? So if we are making this assumption that the distribution we deploy our model on is the same as the distribution that we train our model on, and this actually is not true in practice, what can go wrong? Well, it turns out that quite a bit can go wrong. In particular, one phenomenon that people realize is the case is that somehow our machine learning model, they tend to be really good, they give us very accurate prediction in average case sense. However, these predictions are very brittle. So what do I mean by that? I guess the most entertaining way of kind of explaining is this notion of so-called adversarial example. So what we have over here is a beautiful picture of a pig, which state-of-the-art classifier classifies the pig with high confidence. So everything is exactly as we would like it to have. So nothing interesting here. But things start to get interested if essentially I add certain noise to this picture. This noise is not very big, so essentially the picture after adding this noise is essentially indistinguishable from the original picture to us. But this noise is not random. It's chosen in a careful manner. And what is interesting is that now the picture to the right is to us still the beautiful piggy, but our classifier believes this is an airliner with very high confidence. Okay, so the usual joke is that AI is a powerful technology. It can make pigs fly, but the real problem here is that this is not what we would expect or find desirable. Okay, so in particular, this kind of brittleness was discovered in the context, relatively recently, in the context of deep learning. But really, we did realize that this is a problem already earlier. It just at that time, the average case performance of our models were still bad enough that we did not care that much about what is its worst case performance. Okay. So this is the situation. So there is this kind of very interesting phenomenon that you can add this carefully designed noise to completely trick our classifiers in doing whatever we want. But you might say, well, this is kind of, this is nice, this is cool, but this is kind of, in the reality, you never have this kind of level of fine-grained control to actually like affect every pixel of the image in the way you choose. Okay, so maybe in the real world, this is actually not really a problem because we don't have this control, there's a lot of noise, and in the end, everything works out. Well, it turns out that this is actually not true. So in particular, a bunch of MIT undergrads, what they did, they 3D printed a turtle that, well, looks like a turtle to us, but actually is classified as a rifle, for like by state-of-the-art classifier. So essentially, like almost from all the angles and zooms, it's like actual physical objects, and your classifier would swear this is a rifle. Okay, so definitely you can create these adversarial perturbations in the real world, and there really is something that actually exists. And actually, what was even more surprising to us is that, well, you can create this turtle, but actually the pattern of paint on this turtle have to be very carefully chosen. But it turns out that you don't even go that fancy. So what we discovered is that sometimes even rotations and translations of the object, there are angles and translation of the object that make the predictions really break down. Okay, so you don't have to do anything fancy, you just have to rotate things, and there are certain special angles and translations where you get completely, like drastically different predictions. And again, whatever you say that maybe there will be no bad guys out there who will be painting kind of turtles to make them adversarial, but if you have a visual sensor that gets completely fails when it sees some object under some particular angles, then that's something that you should be worried about. And of course, the first reaction of people when I showed them, they're saying, oh, you just have to do data augmentation, you just have to expose the model to, to different rotations of the objects, but this does not help at all. Essentially, this really still, the model remains brittle. Okay, so hopefully this makes a case that this brittleness of effect in the real world is a thing. And then the question is, should we be worried about this? Okay, so why this is something we should worry about? Well, there is a couple of reasons. So the obvious one is the security angle. Okay, so in some ways, again, as I already told you, so this is another interesting demo. What you can do, there is a face detection system, and what you can do is you can 3D print glasses. That whenever you put these glasses, the system thinks that you are a completely different person. Okay, you can also do this to sound. So you can synthesize, music clips that sound like music to you, but your Alexa device thinks these are voice commands. Okay, so again, this is just your creativity is just what will bound all the ways in which we can fool our devices. But again, even if there is no bad guys, if you just think about safety scenarios, so over here what you see is, okay, let's try it again. So this is just, a trace from Tesla kind of scene understanding software. And actually, as you see, it's actually pretty good, except it, flickers. Like from time to time, you see that things flicker a bit. And again, you might say, what can go wrong with that? Just things flicker from time to time, but most of the time, actually, they are very good. Well, then you go on YouTube, and you have videos like that. Okay, so what's happening here is there is a Tesla car who is on one-on-one, who essentially wants to drive into this divider. And just the driver has to take over to avoid this car running into it. Okay, so again, there is no adversaries here, but these things happen, and this starts to be scary. So that's one more reason why we would like to understand, just how this inherent lack of robustness is actually a problem and how to fight it. But there is also one more reason that I think is important to think about this problem, and actually this will become more prominent later in the talk, is that to me, really, whatever we do with our machine learning models, we really have to understand how they fail. Okay, so every piece of software, every part of the system that we have, they always have some failure modes. That's natural to us, but usually we understand these failure modes. We know how to engineer around them. Somehow for machine learning models currently, these complex deep learning models, we don't really know that, and I think that needs to change. Okay? So these are the reason why we care about this particular brittleness. Yes?
Sure, that's an open question, but do you have any insights how the human visual system do things much better?
Can we ask this the first question towards the end of the class? I don't know the answer to that, but there will be more context for this question. This is a very, very good question. Okay, so this is there are this adversarial perturbation, and that's clearly a problem. But what is even more of a problem is that once you kind of take this more adversarial outlook on machine learning, and you look at the whole pipeline of machine learning, from data collection to training to inference and to deployment, you see that there are all kinds of big gaping holes in kind of how robust and reliable this things are. So essentially, like, it seems that currently machine learning is this kind of best case scenario artifact that essentially, like, on average, everything kind of works. But the moment you try to like get some reliability and some robustness, everything breaks down pretty dramatically. Okay? So essentially, so that's where we are, and kind of the natural question at this point might be, okay, so is ML inherently not reliable? Maybe there is something about ML that it can give us cool demos, but if we actually want to have some reliability and robustness from them, then tough luck. There is nothing you can do. And of course, as you can imagine, the answer is a resounding no. Essentially, what happened is, again, we just never asked machine learning to be robust. We just cared about this, like I would say, proof of concept, average case performance, and that's what we got. So we should not be surprised that we did not get much more. And what we have to do now is exactly, okay, now once we got this proof of concept performance, now we should look back at the whole machine learning pipeline and rethink, what this actually we want from our machine learning models from the point of view of robustness and reliability, and just, get this, definition right, and then try to get towards this goal. So, and in particular, even if you don't feel adversarial, meaning you don't feel there are some bad guys that try to get you, we can think of adversarial aspects as kind of stress testing our solution. So if there are inputs or there is behavior that would actually make your model to break down, you probably would like to know it and ideally prevent it. Okay, so this is kind of the whole agenda of what I would call robust or adversarial machine learning, although I really think that robust machine learning is the better name, is to kind of try to look at all the guarantees that we might need when we actually deploy models in the real world and figure out if we actually can these guarantees, to be satisfied for the models that we deploy. And what I want to do today is I want to kind of give you just a little bit of insight how this data played out in the context of just trying to make the models be more resistant to adversarial perturbations.
So, I've faced this before too, but people make the argument that if we stress test our models against adversarial perturbations or adversarial rotations, etc., we kind of get a guarantee if they're robust to those adversarial settings, they are going to be more robust in the real world settings. Well, the problem we have in the real world settings, there's something like out of distribution samples or things that we have not seen. It's not a fragility.
Yes. So I would like to defer this question because I will answer this question fully, but I will give you a bit more of a thing. But this is a great question, kind of when we say robustness, what we actually mean and how much even we can hope for. And that's something that, again, it's in some ways just like the short answer is it's like with security. Like we never get perfect security. What we do is just kind of we try to delineate the things that we do understand and the things that we don't, and things that we can guarantee to be secure and things that don't, and then just do the best we can. But at least we have a principal methodology to approach toward getting more and more security. So this I presume similarly this is how things progress for machine learning. But again, I will talk a little bit more about this towards the end. Just please remember to remind me. Okay, so we want to talk about how to make models more robust to these kind of perturbations. And well, before we do that, it might actually be worthwhile to spend a little bit of time to explain, how do you actually get these adversarial perturbations? So I kind of show you that there is a way of getting, this, like synthesizing this noise that makes our models misbehave. But how do we actually go, about finding this noise? Okay. So somehow the point of start is kind of, the point of start here is the way we think about the basic kind of goal of training. Okay, so what's happening during training? Well, what's happening is very abstractly is that kind of we have some training example. Actually, usually it's more multiple training example, but we have some training example in mind. And then what we want to do, we kind of want to minimize the parameters of our models, so to kind of minimize the loss on this training example. Again, usually there is many training examples, but for now, just think about one. And kind of the way we solve this task, in particular in the context of deep learning, is that, well, we use the fact that, the networks are differentiable with respect to the parameters. So all I just need to do is I just need to kind of use gradient descent to get a local improvement directions and keep doing this until I get to some satisfactory solution. Okay, the reason why we tend to get to a structured solution is kind of beyond the scope of this class, of this lecture, I guess. This class is definitely interested in that. But again, for some reason, this seems to work, and that's how we train our networks. So that's kind of the good thing about deep neural nets. But essentially, it turns out that exactly kind of the same approach that works for training our models to actually learn can be used to also synthesize the perturbations that might be adversarial towards a particular example. So in particular, what I can do is I can kind of assume that I actually already, fix some parameters of my, final parameters of my trained model, but now I can set up a different optimization problem. So I have a fixed parameters over here, and I have some target input x that I would like to perturb in an adversarial manner. So the way I can set it up as an optimization problem is I actually introduce this parameter delta, which is the intended perturbation. And now what I have to do is just I want to maximize over delta the loss on this example. Okay? So essentially, I just want to find a delta that maximizes the loss of this example. Of course, if I just set up this, this problem just exactly like that, it will not give me an interesting solution, because of course, if I take delta to be just a difference between the current example and example from different class, well, clearly the loss will be very high, but that will not really be an interesting, it will not be really an interesting adversarial example, because the perturbation will completely change the picture. So what you want to do is you want to restrict the the space of perturbations that we actually want to optimize over. And now this is actually a very active and very good question of what are the perturbations that we should kind of consider here. So the most basic choice is just to kind of make sure that the pixel-wise norm of the perturbation is small in some LP norm, and that's going to is the most basic way to do it. But of course, the additional, you realize that just doing this LP, being robust to LP perturbation does not exhaust all the ways in which I can modify the picture to make it to make it essentially the same to a human, but different to a machine. So you can add rotations, you can get some VGG feature perturbations, and the list could go on, because in the end, the complete list would need to specify exactly what is similar to a human. And we don't know how to do that. So, this choice, so all I want to say is that this choice of this of what is the set of delta, of perturbation delta that I want to consider is very important, but I will put it aside, for this lecture, because that's really not the point of what I want to talk about. And, in any case, I guess just that, being robust to small LP norm is clearly a necessary condition. So let's just focus on this kind of robustness for now. But it doesn't, by far, I'm not claiming that this is end of the road. It's definitely not. Okay? So now we know that, so we would like to get a model that is actually robust to this kind of, LP-bounded perturbations. So how can we go about this? Well, in a sense, the key observation here is that, and this is something that people, I think, it took a while for people to realize, is that the fact that we are not robust to adversarial examples is not in any way a kind of a failure of our machine learning framework. Okay? Because essentially what our standard machine learning framework asks about is kind of try to achieve this standard generalization. Okay? So what it tried to do is just saying, okay, if I sample an example from my distribution in the sky, and I look at the loss of my model on this example, I would like this loss to be small in expectation. So this is kind of what our standard toolkit was trying to achieve. And actually it succeeds quite spectacularly at getting this kind of guarantee. The only problem is that this adversarial noise is like a needle in the haystack. So essentially, this kind of statements about expectations, they have no real power to bound the existence or lack of existence of adversarial perturbations. So, well, that's a problem, but also that also tells us what is the solution. Okay, so we have to actually ask for more. So we have to actually change what is even the whole goal of our training. And and one natural way to do it is do something called adversarial robust generalization, in which what I want to do is I want to have the guarantee that if I sample an example from distribution, and then I look at the loss on the worst case perturbation of that input, I want this loss still to be small in expectation. Okay? This statement already tells me something about robustness to adversarial perturbations. Okay, so now, importantly, we know now what we are after. We would like to get kind of generalization of this kind. And now the question is, okay, how to get there? But honestly, at this point, it's very natural what to do now. We just essentially repeat the story that we had for, for standard, like getting standardization. So of course, we cannot evaluate, we can't optimize over the population risk. Okay, so this the robust population risk. So we optimize over the empirical risk. So essentially what we do, just we look at our training set and we try to make sure that you get you are able to, to robustly classify everything in this training set. So the training problem that becomes now, it's no longer just a pure minimization problem, it's now the min-max problem, in which the inner optimization problem corresponds to finding a bad perturbation for a given training example, and the outer optimization problem corresponds to finding parameters for a robust model. Okay? So at this point, as long as you believe that, like minimizing this empirical robust loss will actually lead to also, robust generalization, this is just about optimization. Okay, so, and indeed, like the natural algorithm to solve this is just by using essentially alternative minimization. So what you do, like in machine learning terms, is that essentially whenever you take the next batch of training examples, what you do before you pass them to the model to update parameters, you actually find the worst case perturbations for them, and you update the model on these perturbations. Okay, and just you keep doing this. So this is something called adversarial training, and the question is, it's very intuitive to do this, but does it work? And the answer roughly is it works, at least in practice, but you have to be careful how you do it. So essentially people tried similar ideas before and it didn't work because there are certain things that are important to get right. So the long story short, like the things that you need to really be, you really need to get right is, first of all, you really need to be able to solve this inner optimization problem reliably well. So you need to be able to get good solution, like the truly close to worst case perturbation for each of the examples you are trying to perturb. And also the other thing is that actually you seem to need sufficiently large capacity of your model. This seems to be another thing. And this is actually a thing that I still don't understand exactly why. But it seems to be, at least empirically, that you need to have a large enough model to even be able to express these robust classifiers. But once you do it, at least in practice, everything seems to start to work. You are able to increase the robustness on your training example, and it turns to generalize to the test set. And just over here are just some of the example configurations of the perturbations that we might want to have, and on different training sets. As you see, so this is like the accuracies, like the robust accuracy on the test set. Clearly, we would like all these numbers to be 100%. They definitely are not 100%. On the other hand, they used to be 0%. So essentially, we are making some progress here, but definitely we are not there. Yes. Well,
it's kind of data augmentation, right here.
Okay, so I will get back to this point, but remember there's an important difference. When you do data augmentation normally, you just take random rotations. Now you choose worst case rotation each time. And that's the crucial thing. So essentially, in terms of optimization, with data augmentation, you solve this problem by just choosing a essentially random solution. And it's usually not the worst case solution. And here you are actually trying to find the worst case solution. And that gives the signal to the model. Essentially, that's what really drives the optimization of this problem. That's a great question. Let's just, I will get back to that. That's a great question. Okay? So this is if you just are here for safety and security reasons, I might just stop this lecture here. But, if you are a more machine learning minded person, you probably should get more intrigued than what was just asked, is essentially, is essentially one of the questions that I started asking myself. So essentially, okay, so if you care about security and safety, this is where I could end. But to me, actually, this is where things start. Okay, so essentially, at this point, you sort of defined a new kind of machine learning. Okay, so you have now, the standard machine learning, which is about trying to achieve this standard generalization, and then there is this robust machine learning, which is about trying to achieve this robust generalization. So, the question is, how differently, what are the properties of, this robust machine learning versus the standard machine learning? How things like average, the average case error, how do they evolve and how do they compare? Okay, and again, just one point that I really want to make here, even though it might seem otherwise, this problem is not really about deep learning. Okay, deep learning was the setting where we discovered that this is a real problem, and deep learning is nice to work with because it's easy to find these perturbations. But the same problems are true for like boosted trees, for linear classifiers, for anything. Essentially, this is just really a question about I am after different guarantees, and essentially I get different properties of the classifier I get if I'm trying to get different guarantees. Okay, so that's the kind of that's the kind of outlook that you should have here. Okay, so now we want to understand, we want to compare some of the basic fundamental kind of laws of standard machine learning and the robust machine learning. So the first question to ask is, okay, so do robust deep network overfit? Okay, so as you remember, and I'm sure already many people talked about this, if you look at the kind of standard setup of machine learning, we know that the picture goes like this. So saying, okay, if I want to train my classifier on the given data set, well, I optimize the empirical risk, and quite quickly I get to 100% accuracy on my training set, and then now I see what happens on the test set, and luckily, the loss or the kind of the accuracy that I get on the test set is actually not much smaller than what I got on the training set. So essentially, like we say that the generalization gap is small. Okay, so that's how deep learning in particular seems to work. But how does this phenomena look like for robust models? So in particular, so imagine I actually really I train my model to get 100% robust training accuracy. So I want to robustly classify all the examples in my training set, and with some work you can do that if you take big enough network. But now the question is, okay, so I want to care about my performance also on the test set, not only on the training set. But unfortunately, if I look at what happens on the test set, then actually I have this huge generalization gap. Okay, so essentially it turns out that somehow here my kind of empirical loss accuracy grew together with the test accuracy, but here I was able to kind of essentially overfit to the training data, but I could not get any generalization out of that. Okay, so what's happening? Well, that's a good question. We don't exactly have have an answer. So of course, the first thing you try is to try to different regularizations. Nothing that we found could really help. And then we kind of realize that there is another reason, another potential explanation why this is the case. And kind of the explanation was that actually, if we talk about this goal of robust generalization, then essentially the sample complexity of robust generalization can be much higher than the sample complexity of the non-robust of the standard generalization. So essentially, this is the theorem, and I will not get in exact bounds, but essentially what you can show, and this is not really hard, is to show that there exists a d-dimensional distribution D, just essentially two Gaussians, such that if I just take a single sample from the distribution, I am able to get a classifier that kind of is correct on with probability 0.99. Essentially, so it's essentially generalized in the standard way very, very well. However, unless I will see at least square root of D independent samples from this distribution, I will not be able to come up with a robust classifier, in the information theoretical sense. So essentially, it's impossible for me, in information theoretical sense, to actually be kind of essentially any non-trivial robust classification. Okay, so essentially, so if you just care about linear classifiers, you can just take a simple distribution of the hypercube, and if you want to get this result for any classifier, including nonlinear ones, then you just have to do Gaussians. So honestly, the proofs are not very difficult. This is the point. This is more about just making the point that you do indeed need to have a very different sample complexity. And indeed, in practice, we do observe that if we look at how these things behave as a function of the size of the training set, it seems that the point where our generalization starts to ramp up for robust generalization is much further. It starts at larger sizes of data sets than what we observe for standard generalization. Okay, so there seems to be something interesting there. Again, I'm not claiming this fully explains the phenomenon, but this is just one of the preliminary things that we discovered. Okay, and now essentially we go back to your question here over here. So essentially, so somehow my belief is that if we can get a robust classifier, it can only be better than the standard classifier. So let's see about that. So in particular, does being robust help with standard generalization? Okay, we are kind of asking our model to do even more. Does it mean that we do very well on standard generalization? So kind of the intuition here would be that in some ways, as already someone said, you can view this, essentially, well, you can view the adversarial training as kind of this ultimate form of data augmentation. Kind of, it's not only that you just show the model like random transformation of your input that might confuse it. You actually choose the most confusing transformation of your input and you show it to your model. So that should be even more helpful for the model to understand the concept you are trying to learn. So yeah. So does it mean that the robust models will also be better, in terms of standard generalization? Well, let's look at the data. So yeah, over here we have essentially the test accuracy of a standardly trained model. So you see that like the more we train, the more this accuracy goes up, and at some point it plateaus. However, if we look at the same data set and we train robustly, a classifier, but we look at the average case performance, then you see that it's not only that we don't get any improvement, we actually seem to always have a gap. Okay, so it always seems to be worse than what you get with standard classifiers. Okay, so it's robust, but its standard performance is much worse. So, where is this consistent this consistent gap coming from? So why is it the case? Again, at first I must admit that it was surprising to me, but then you think a little bit and then you realize this is not surprising at all. Okay, so essentially, the point here is that the basic intuition behind this gap is that it's very easy to construct distributions that have this kind of behavior. So essentially, the basic intuition here is that when you think about the standard training, what you really are doing in all of this deep learning is really you are trying to extract the correlations between different features in the data and the label. And when you think about the standard training, all the correlations are good. So anything that has some correlation with the right label is useful to you. However, when you talk about robustness, you actually must avoid some weakly correlated features because essentially the problem is that if you your decision depends on too many independent features, the adversary, for different ways of for different threat models, for different perturbation models, can actually use it to to accumulate essentially to influence your decisions in a big way. Sorry.
What do we mean when we say weakly correlated?
Sorry.
Yes,
so I will say an example. Yeah. So let me just be concrete. So this will be this will be the example. So imagine we have the following distribution in which each input feature is just independent feature, and we have one feature that is strongly but not perfectly correlated with the label. And then there is a bunch of independent but weakly correlated features. So essentially, each one of them is, let's say it is actually correct label probability 1/2 plus some tiny epsilon. Okay, but you use many of independent them. So now, from in some ways, what is nice about these weakly correlated features is that they aggregate to if you think about the law of large numbers, they're independent. So if there's enough of them, they actually aggregate to one very strong feature. This has a very strong correlation with the label. And essentially, in standard training, what happens is actually you will figure it out that essentially, if you look at the sum of these features, it's a very strong kind of meta feature that actually correlates very well with the label, and you will just use that. However, the problem is that this meta feature is very accurate, but it's also non-robust. So if you think about the adversary that can perturb each one of them just by a tiny bit, essentially by just perturbing them by a tiny bit, the adversary can accumulate strong signal that completely shifts this feature from being positive to negative and completely manipulate it. So essentially what has to happen is that when you do adversarial training, so when you train a robust model, then essentially it will realize that you can't rely on these features, and what you have to do is essentially you only can rely on this one single feature, which is strong but not perfect, and that's where the gap comes in. Sorry, what is
the nature of the test data set that you're using?
What do you mean by nature? So this is just a synthetic data set. I just want to show, this is a completely synthetic distribution. And I could create from this a training set by taking some samples to my training set and then have more samples to the test set. Is that?
You train your model on the samples that get perturbed so that you want to develop this robustness and then omit eventually weakly correlated features. But
Uh-huh.
when you construct your test data set, maybe it should be
So notice that, okay, so first of all, like, I just define a distribution, and once I define distribution, like the construction of the training set and test set is automatic. I just take some number of samples to my training set and some number of samples of test set. So what you are saying is exactly you are trying to see, okay, how would I construct a robust model here? And in particular, like if we apply the robust training.
How can we test robustness?
Oh, well, how we'll take robustness is kind of, in some ways, by trying to attack the model. And essentially, like, so what you do is just like you look at the test examples and you try to attack each of the test examples and see if you are able to flip flip the prediction of the model on, in this way. So that's how you test it. Again, how do you get guarantees that this actually happens? Is that if you don't find a bad perturbation, that actually there is no bad perturbations. That's a separate question, but yeah, it can be done for at least for not too big models. Okay. Okay, great. So again, well, this is not, this was not something, something too sophisticated. It's just to give you a concept like how this, optimizing for worst case performance might actually necessarily mean that you have to compromise the average case performance. Okay, and this seems to be happening in the real world. So it's not only on this synthetic distribution. This kind of behavior seems to be happening on our real data sets. Okay, so somehow the summary here is that kind of there is this kind of notion of like robustness is not for free. So clearly, we have to pay because the optimization, like the training, the training process is expensive. It requires larger models, so that's one kind of cost that we pay. But there is more. So we know that we might need, and actually we do need more training data to to get robust, do robust generalization. And also we might need to necessarily kind of give up on the standard measures of performance to get some robustness. So this is kind of this is the kind of picture we get. Yes.
If your classifier is a linear classifier, adversarial training is equivalent to lasso, right?
Yes.
It's also a feature selection, but in traditional statistics, feature selection will always make my prediction better. Why here it becomes
That's an excellent question. Again, just bear with me. So the point is like exactly the question is what better means. And you are right. But in some ways, there is better and better. So essentially, like if you just think about average case performance on the test set, then that's what I'm saying is happening. But the question, if this really means being better, that's exactly the question that actually we are getting towards right now. So that's an excellent insight. Okay? So this is kind of, so you can just like have this kind of, this is some very basic properties of like how robust models seem to behave a bit differently compared to the standard models. And, and you can do more research in this vein, and people do research in this vein. But, as much as I had fun discovering this, these things, kind of what I realized is that like, okay, so these things tell me, how robust models behave and kind of what happens when I compare robust models to non-robust models, but it does not tell me why. Okay, so it doesn't really like give me the satisfactory answer to why. So some of the why questions here are, first of all, why adversarial perturbations exist and why they are so widespread. Okay, so again, it's clear that we never try not to have adversarial perturbations, but so yeah, we cannot expect that there will be none of them, but like why there is so many of them, it's extremely easy to find adversarial perturbations for our classifiers. The other question that is even more mystifying is that it's not only that for a given input and given model, I can find a perturbation that makes this model make this model misclassify. It's actually like if I take a random adversarial perturbation for one model, it has good chance of working towards completely different model, like a model with completely different architecture and trained independently. So this is kind of the mystery that somehow this noise, even though it seems that it should be very specific to the model, it actually doesn't end up being so specific to the model. And the other thing is kind of why does robust training work? So, okay, I can understand how I can get robust classification of the training inputs, but why does it mean that I actually get generalization? Like, why does it also seem that I robustly generalize inputs that are not in my training set? Okay, so these are kind of the three things that were mystifying me. And let's try to, see if we can get some answers to that. Okay, so why do adversarial perturbations exist and why they are so widespread? So again, definitely, like this kind of question I was not the first one to wonder about this, and there is like plenty of hypotheses given, like why our models are brittle. Some of them just talk about, okay, our models are high dimensional, so there are always some corners that kind of where the models behave. Others say, well, our training set is a sampling of some distribution, so there are always some fluctuations that kind of make the model kind of have some, like there is some tail that makes our model misbehave, and that's what we are exploiting. The others say what I just said, saying, okay, we never optimize for robust performance performance. So, well, why would you expect otherwise? And also there are kind of, statement that says, oh, this is just a punishment for using resness, or the punishment for using batch norm, or whatever is the technique that you don't like, that this is probably the reason why we have it. Okay? And somehow all what these explanations have in common, they really view adversarial examples as aberrations. Essentially, there are evidence that we did something wrong, or kind of like our learning is not perfect. And kind of this is why we have adversarial perturbations. So let's think about that. So before we think about that, let me move a little bit more into I would say almost neuroscience, and just try to think a little bit more about why are adversarial perturbations bad even? Okay, so what is so upsetting about adversarial perturbations? Well, what is upsetting is that I can have this beautiful picture of a dog, and I add some meaningless perturbation to it, and then I get a picture of that is something that looks like a dog to me, but the classifier insists this is a cat. So this is really upsetting because how could this meaningless perturbation change the meaning of this picture to our model? This is really not the right thing. So this is what upsets us about adversarial examples. But the point of start I want to make is that this is it's upsetting, but only from a human perspective. So what do I mean by that? Well, essentially, if I look at the most important classification task in human history, like cats versus dogs, so essentially, we as humans, we know how you are supposed to solve this task. Okay, so you are supposed to look at things like snout, shape of the ear, and based on that, if this is a dog and cat, and that's how we solve this classification task. However, it is less clear what is the machine learning model perspective on this task, because to this model, it has no notion of an image. To it, this image is just a sequence of numbers. It's there is no inherent understanding of the image beyond confidence, maybe, that we imbued the model with. So this is it doesn't understand that this is a depiction of an object in the real world. And the other thing, the class dog is completely meaningless to it. This model has no concept of a dog. To it, it's just a string of character that is supposed to correlate properly with the string of numbers that it's getting as input. And that's the only thing it cares about. It only cares about passing this accuracy test at the end, that whenever it gets queried with a sequence of numbers, which is the image, it wants to output the right sequence of characters. That's all it cares about. So somehow, if you are from this perspective, talking about the dog versus cat classification challenge is a bit misleading because, again, we as humans know much more about this task than this poor model does. So maybe in order to visualize a bit better how machine learning models approach this task, let's think about TAP versus TOC classification. So what is TAP and what is TOC? I have no idea, but that's exactly the point. That essentially I just can notice maybe after some time that there is whenever I get this structure in this rectangle, then this is the TAP class, and whenever I get this structure in this example, this is a TOC class. But essentially this is just a simple correlation that I can learn, and I don't know anything beyond that about this task. And when I think about, instead of dog versus cat classification task, I think about adversarial examples for TAP versus TOC class. Well, somehow these adversarial examples seems much less upsetting than the classification task over here. In particular, it's no longer clear to me that this perturbation is meaningless. To me, everything is meaningless. So what do I know? What is actually meaningful or not? Okay. And somehow, again, this is, of course, just a fun way of making a leeway into the question that I actually want to ask. And this is the question that we ask in a recent paper, this question is, okay, so intuitively, when we see this noise that we are adding to our images to change their prediction, they are clearly meaningless to us. This is just a noise that we it has no meaning to us, so it should not change the prediction. But is this noise actually meaningless? Okay, so let's try to think about that. So let's do the following simple experiment. So let's take some standard training set of cats versus dog. Okay? So essentially I have a training set which has some examples of cats, some examples of dogs with correct labels. And what I will do now is, well, I will train a model on this training set. And now I will use these models to create a new training set. What will be my new training set? Well, what I will do is I will take every example of a cat from my original training set, and I will find an adversarial perturbation that makes my model believe this is a dog. Okay, and that will be my new, essentially I will adversarially perturb every cat into a dog, and I will adversarially perturb every dog into a cat. And now I will have this new training set in which what I will do is I will take this adversarially perturbed cats and dogs and I will label them as such. So essentially every adversarially perturbed dog I will label as cat, and every adversarially perturbed cat I will label as dog. Okay? So I have now a new training set, which kind of has this, adversarial perturb cats and dogs only in it. Well, that's a new training set, so I will train a new model on this perturb training set. Okay? I will train the new model, and then what I will do is I will test the performance on this model on the original test set. Okay? So this is kind of a little bit, this is kind of maybe a little bit confusing, so let's go over this slowly. So essentially what is happening here, in this training set to a human looks completely like mislabeled. Like essentially like every input that looks like a dog to us is labeled as a cat, and every input that looks like a cat to us looks like is labeled a dog. So essentially, in particular, if you didn't speak English, and I will just give you this training set to learn, you would conclude that that dog is is a cat in English, and cat is a dog in English. Okay, that's the conclusion that you would like to do. But now the question is, so our performance on this test set will be, of course, 0, because we would always get, exactly the opposite prediction. But what will happen if I actually run this test on my model? So if instead of a human, I actually ask my model to train on this mislabeled data set and then take a test on the original test set. Well, what happens, we are actually getting quite non-trivial accuracy. So in particular, on the CFAR version of this challenge, we get 78% accuracy. So not 0, but actually 78%. So somehow, even though we never shown the model a single cat labeled as a cat and a single dog labeled as a dog, it kind of almost figured it out completely, like which one is the cat and which one is the dog. Yes? Then you get 0. No, well, then it's actually 0 because it's actually it's not only because you learn the opposite thing, so it's not even random. But yeah, you can also have a version of this when you have multi-class and then you do random labels, and then you would get 50, we would get random guess. So the crucial thing here, okay, so that's the question. So what's going on? And essentially, if you start thinking back, okay, so what was these assumptions that led me to the conclusion that it should be 0%, it wasn't? The only assumption that you really made was that, the adversarial perturbations were meaningless noise. And that's clearly not true. They clearly are conveying some important information about the, about the task.
What happens if you do robust training?
With robust training, then essentially you get 0. Okay, so which again hints at what's going on. But that's a very good question. We did that as well, and then you are getting some, essentially this is just a nicer way of doing it. But that's the point. So kind of the point is that what if these perturbations are not just some noise, meaningless noise, but actually they correspond to meaningful patterns in the data. Okay, so somehow this is what we call, again, just conceptually robust feature models, in which kind of there are usually when you think about learning as humans, we really think of features that we will call robust features, or things that there are features in that you can extract from the patterns in the data that that you can extract with the features that are robust, that are first of all predictive. They actually correlate with the correct label, but also are robust under the small perturbations. So this is the things in particular anything that human uses falls into this category. Okay, because we tend to be our classifications tend to be robust to perturbations. However, and this was a surprise, it turns out that apparently there is a vast spectrum of patterns in the data that are also very predictive of the correct label, but are actually non-robust, that actually can be completely flipped by just adding, let's say, tiny bit of L2 bounded noise. And kind of what happens is that, well, our models just care about maximizing the accuracy. So any feature that helps them get the right answer on the test is a good feature to them. And well, it turns out that these non-robust features are actually often great. The total the correlation, the information you can extract from this feature is actually even stronger than what you can get from robust feature. And that's why our models gravitate towards picking on them. And that's why also they become adversarially vulnerable, because now if their decision process depends disproportionately on this non-robust part of the signal, well, the adversary can just flip these things and make the model believe that something opposite is happening. So again, so this is kind of can sound very mysterious. So just the way I like to conceptualize this notion is just imagine the following, which again, this is not what's happening in the real world, but this is just a way to conceptualize, is that imagine that someone, for some reason, the top left corner pixel of every image of a cat and a dog, both in the training set and the test set, has a color that is red if this is a dog, and it's green if this is a cat. Okay, so for some reason that happens. Just imagine that this is true for all of data, not only of the training data. Then what will happen? You as a human, if you want to learn cats versus dogs, well, you will not notice this pixel at all. So you will ignore it, and you will just do whatever usually you do here. However, what our model would do, it would almost 100% or really 100% depend, or just read off the color of this corner, and make this prediction out of that. So this way, it actually would get amazing performance on the test set, because the test set has also this correlation. But it will be also extremely brittle, because I can just change this, the moment I change this pixel to a model, I change completely the prediction, I flip the prediction right that. Okay, so this is just kind of a one way to try to internalize what these non-robust features might be. I'm not saying that this is what they actually are, but this is the closest I could the concrete example of how this could, how to think about these things. Okay, so now if this is the model of the world that we have, we kind of start to make sense what happened in this experiment. So what happened there is that we had this robust features and non-robust features that were kind of in agreement with what is kind of they were predictive of the correct label. And what happened in our new training set is that the robust features were now misleading. They were really misleading us, but the non-robust features were still kind of aligned with the right label, and they were, and they suffice for good generalization. Okay, so yeah, that's okay. Okay, so this is kind of the main message I wanted to send today, but let's try to think of some of the consequences of what this means. So one point is this human versus ML model prior. So in some ways, again, if you think of some particular classification task, we kind of, as humans, tend to assume there is only one way to solve it, because our way is the right way, clearly. Well, it turns out that, and again, and for people who actually do statistics, this should not be surprising, is that there are many ways of solving these classification tasks, and many of them turn out to be very different to how we think it's possible to solve it. So essentially, since all this, anything that gives you the good performance on the test set is valid, valid way of doing it, there is no reason why we should expect our models to use the classification method that we as humans like, as opposed to, what the model thinks is the most effective to get the test right. So that's kind of one point to keep in mind. This in particular means that adversarial examples are really there's nothing inherently wrong with adversarial examples, when they actually exist. The models don't do anything wrong. The only thing that is wrong about adversarial examples is that they are it's a misalignment. It's about humans. It's just saying the only thing that they really show is that the way the model makes decisions is different to how we humans make decisions. Okay, so that's kind of the driving factor here. In particular, this kind of comes up in the context of interpretability, which is kind of a big thing nowadays when we want to apply machine learning in context that matters. So people kind of view interpretability as a post hoc method, meaning you train your model, then you give it to me, and I will find you the explanation why a model did what it did. Well, what we know now is that the way the model reasons about makes decisions might be very foreign and incomprehensible to humans. So if you do it as a post hoc thing, well, the explanation that you will get will be, you will not understand what it means, or if it makes sense to you, maybe it's lying to you essentially, and you are missing some important factors that go into the decision of the model. So if you want to have interpretability, you have to think at the training time to make sure that the decision process of the model is aligned with with something, with a mechanism you could as a human understand. Okay, and that's something that really you have to plan ahead of time. So in particular, you need additional restrictions, priors on what features your model should use to make a prediction. And again, this goes back to the thing about again in statistics. This is well known. It's you have to do some feature selections. You have to think about kind of what it is that you want to base. What are the right ways to learn from the from a given patterns. Which patterns are actually good to use, and which ones actually are the ones that are kind of they look tempting, but they actually are not the right thing. They are kind of they are misleading. Okay. So yeah, so what now? So well, what is nice now that kind of we get this new perspective about kind of adversarial robustness, and we also get insight into all the other questions that I asked before. Okay, so for instance, if you go back to transferability, well, now it makes much more sense because essentially features, like what kind of patterns are in the data set and what kind of features would extract this data set, well, this is a property of the data set and not of a particular model. Like, and if the patterns are in the data set, and different models, if these patterns are very useful for classification, will tend to gravitate towards them. So essentially, that's why kind of the same perturbations that correspond to flipping these patterns, they actually work for different models, because different models kind of latch on to the same patterns. So, and again, we did some experiments, and indeed, you can see, we can see that exactly like there is this correlation between kind of transferability and kind of how non-robust your model is. Okay. Actually, it really this seems that the kind of the natural adversarial examples that appear in the real world, the one that transfer, they really seem to correspond to this non-robust patterns in data. Okay, so the other thing is going back to the robust training. So essentially, in some ways, it was unclear to me why robust training actually leads to robust generalization, and now it makes a bit more sense, because essentially, whenever we kind of solve this max problem, each time we update the model weights, what we are really doing is that we kind of force the model to never depend on any features or on any features that can be flipped by small perturbations. So we essentially are penalizing the model whenever it tries to make its inference using features that are fragile to the kind of perturbations that we want to be robust to. Right? Because we are always finding, okay, if you depend, if I can change your decision by small perturbation, it means that I found, kind of part of your decision process that is really depending on patterns that are, very fragile to the perturbations. So this way, what we are really doing is robustness is just like a regularization on our model that kind of tells it the only way you can make inference is based on patterns that are robust to the set of perturbations that you are doing. So, and clearly, if this is the only way you can learn, then whatever you learn will generalize in a robust fashion to other data. Okay, and also some of the findings now they make even more sense. Essentially, what they say, because so what happens is that robust models can only leverage robust features. So in some ways they are handicapped, right? Because we know that these non-robust features are actually very useful for generalization. So this means that yes, we need more data to get the same accuracy than non-robust model. The non-robust model, we also might fundamentally just be able to attain only lower standard accuracy, because there are some signals in the data that we are not able to latch on. So and there is also in the paper we have some nice kind of toy setting to kind of just try to visualize this phenomena. So this is robust max likelihood Gaussian classification, which again it's something where you can just work it out. It's simple enough that you can actually work out the math, and you can see all of this kind of phenomena that we talk about emerge there very naturally. Yes, so that's a great question. So in some ways, the even more basic question is okay, so we just kind of proved that non-robust features exist. The question is, how do they look like? What are they? And we kind of don't know yet. So this is something this is the frustrating part, that we kind of cannot pinpoint what these non-robust features actually are. Again, I can tell you about this pixel, but clearly that's not what's happening. Leon Batu, he had this nice idea that kind of, the optical system of our camera might kind of distort the image differently depending on the exposition time and how, what kind of zoom we are using. And for instance, for dogs, we usually photograph them from a bigger distance. They are in motion, so we the exposition time is shorter. Cats are inside, so in particular, we photograph them from closer, and the exposure time is longer because there is less light. So maybe this is one example of some of the non-robust patterns that actually are predictive of the right class. It's just not something we as humans would actually be able to do, and it's potentially easy to perturb them into change one configuration to the other.
One thing is if these imperceptible features that exist in real data are so easy and so correlated in their cost, why do deep models even bother to learn human objectable features in the first place?
That's a great question. Again, so what our experiments show that definitely it seems that they assign more weight to non-robust features than the robust features. But again, if the robust features are independent of non-robust features, they are still helpful. right? Like there is no reason not to do it as long as these things are independent. Just say you don't have any inherent preference for robust features, and it turns out that you can learn quite a bit from non-robust features, and that's why they're using them. So kind of this toy model I mentioned, that when there's just one strong feature and this many of these like weakly correlated features, is a good way to think about it. Like saying in this way you kind of, okay, so in that example you really get already a lot of information from just these weakly correlated features, but you could also, you know, include this like last feature there as well. It definitely will help. The question is like maybe not too much anymore, but it will help. So that's kind of the effect that's happening, I think, in our models. Okay. So yeah, so we don't know what the non-robust features are, but let's try to look what kind of properties the models that actually don't use them have. And it turns out that they are actually quite nice, not only because they are robust, but also from the point of view of machine learning. So in particular, the vision model that you are getting here, they end up being quite more human aligned than our standard model. So just one way to visualize this is kind of like, so essentially like one way people kind of use to understand, you know, why, get some insight into why given model made some prediction is to look at the saliency maps. So what I just do is I just look at every pixel and I just want to see how much changing this pixel can influence the prediction for this model. And this gives me this heat map when I kind of color each pixel proportionally to how much influence it can have on the prediction. And if you do it with standard models, you're getting things like that, which clearly like some parts of the image that, well, should have some impact, they have, but also it's clear that you also depend on things that are not even part of the dog anymore. And they seem to be influential as well. So, but, you know, if you do it to these robust models, you know, without any regularization, any kind of trying to beautify it, you are getting saliency maps like this, which again, look much nicer and closer to what a human would actually draw. Okay, so the way to think about this, you can view like this robustness as kind of as a prior that kind of tries to align our representation to be closer to what, like, you know, the representation of to the things that human perception registers. And this goes further. In particular, you can show that. So one thing about kind of our standard neural nets is that kind of we have this like second to last representation layer, which kind of we want to think as the high level features of the data that the model kind of figures out. And this kind of seems to be the case, except what happens is that, you know, it's very easy to find two images that are completely different to us, but seem to map to the same representation. So this shows that this kind of this mapping between representations and, you know, the actual data is not exactly like, you know, it's not reflecting exactly the right geometry. However, somehow with robust models, we were at least unable to find two images that map to the same representation, but are different to humans. So essentially, like, it seems that you necessarily, like, the only images that are close in this representation space are the things that are actually close to us humans visually. So kind of this fixes quite a lot of problems with them. So then you can do things like, you know, essentially like, well, feature visualization. So this is like interpolation. So you can do interpolation very easily. You can also kind of look at individual neurons, and they tend to have some, like, well, human understandable meanings, just somehow naturally, so that you get this nice disentanglement of features that actually make sense to human. And also you can do all this kind of funny things. So like once you figure out what is the neuron that corresponds to detecting stripes, what you can do is you can want to synthesize a version of a picture that excites this neuron even more, and that's the way you can essentially add stripes to a dog. Okay, so essentially you just say I want to see the same picture, but in a version that makes me detect stripes, and that's what the model essentially helps you find. Yes. So essentially what you do, like optimization-wise, what you do is like you treat you do the same things for example. So you kind of parameterize the perturbation of an image as a variable, and then you say, oh, I want to find the perturbation that makes this neuron more excited. And when you do it, it ends out that the perturbation that adds stripes to the dog is the one that actually ends up exciting this neuron more. Okay, so there is a lot of other stuff. You can get essentially generative models that kind of, in a very simple way, that kind of you just fit some simple Gaussian model to your kind of representation data, and then sample from it, and you are getting some kind of really nice generative model. So I'm sure all of you know about GANs. So I think 3 years ago this would be like state-of-the-art GAN, GAN development, but it's like super easy to do it as opposed to GANs being very difficult to train, and we still don't know if they actually learn the right distribution. And you can do like super resolution in painting, and also you can kind of do these cool things where you kind of can, sorry, just let me. Yeah, you can do this kind of morphing like one class into the other, right? So you can either take a sketch and make it more photorealistic, or what you can do is you can take a like morph a dog into an ape. You can morph a this was like the ananas into like some animal. You can do all of these things, and all of this is just driven by the representation that you just found. Essentially, what you are doing is like very simple optimization where you just say you start with a general image, and then you just want the classification of this image to become more of a different class, and that's what the model does. So you can play with the demo online. It's actually quite a lot of fun. Okay, so far this was a lot of fun, and kind of we talked about this robustness, and this seemed to be the desirable things, but is it only about robustness? So kind of like, so this was, again, when I started being in this field, I only cared about security. And then I kind of started talking about, thinking about reliability. And then I kind of tried to understand, okay, how robust machine learning differs from standard machine learning. But kind of the more I went there, I realized that this is about something even more kind of basic than just, how to be robust or not. And in some ways, kind of, it's about trying to understand how our models work and what is the right way of learning from data. Okay, so what do I mean by that? So in particular, I told you that there are these kind of correlations in our data that are useful for classification, and a priori you think, okay, if there is a correlation in our data that is useful for learning, if I can take advantage of it, I should. But only later you realize that, well, this correlation can be weird. So for instance, like one correlation that seems to be the case in the ImageNet dataset is the kind of that whenever people put bow ties on their pets, it seems they're more likely to put it on a cat than a dog. So again, clearly this is a useful signal. Whenever I see a bow tie on a pet, this increases the chance that it's more likely that this is actually a cat than a dog. But then if you think about it, like, do I really want my classifier to depend on this? Like, essentially, if I actually wanted to train a classifier that distinguishes dog versus cats, should I actually rely on whether there is a bow tie there or not? And similarly, as I already said, this kind of, we tend to photograph cats inside and tend to photograph dogs outside. So looking at the background is clearly a strong signal on which one it is. But this would be like, this is the usual anecdote about the tanks. During the night they are not on the they're not present, and during the day they are present, and that's how you know whether there's a tank in the picture or not. Like, so this is the same phenomenon. Like, we don't really want to depend on the spurious correlations. But again, this is just fun. Like, this is just cats versus dogs and bow ties, so this is all fun. But it turns out that it becomes much less fun in the real world. So now there is a lot of excitement about using, in particular, deep learning for like medical imaging. So essentially, you would like to be able to train a classifier that, given an X-ray, it kind of recognizes, let's say, if this person has tuberculosis or not. Sounds great. And people do that, and they get this classifier that seems to outperform all the physicians at this task. But then people look a bit closer, and what they realize is that actually the way this classifier makes the prediction, it actually, one of the important inputs for this model is figuring out what was the machine that took the X-ray, what type of a machine took the X-ray. Because for tuberculosis, for instance, it's not like in developed countries, it tends to be very rare. So many of the positive examples actually are coming from less developed countries, which have older machines. So, by just knowing what is the type of machine that took the X-ray, you actually have a pretty good idea if this should be a positive example or a negative example. That's what you learn, and that's what you're asked to do. Similarly, there is another study which showed that there was a app that was trying to detect if this is like the dangerous change on your skin or not, or benign. And again, it turns out that the presence of a ruler in the picture was again a strong signal to figure out which one is which. So, so this is kind of something where, kind of this fact that there are correlations that seem to be helpful, but actually are very misleading. Like, this is much more serious setting in which kind of you have to think about it more clearly. And kind of what is nice about robust models is that, again, this is a problem that will always be a problem. Like, that's, again, what statistics, that's what data science is about. It's exactly trying to play with these kinds of patterns, deciding what patterns, to use and which patterns not to use, and how to clean up your data set and regulate your model to make them learn the right way. But there is just some interesting thing that the robust models seem to be able to do that maybe will help, at least as a partial tool. So essentially what you can do is, so here we have an example of a picture that for which the correct classification is insects, but for some reason the robust model claims this is a dog. Okay? And you may say, well, whatever, we are not expecting our models to be always right, but maybe you would like to get a bit more insight into why there is such a prediction. And one way to do it is kind of something very simple. What you can do is kind of you can say, okay, can I morph, like you essentially use the model to morph this image into a model that is kind of, that excites the neurons responsible for the dog prediction even more. So essentially you are asking, can you show me how would this image change if it, to become more dog-like to you? And when you do that, what you will get is you will get the picture on the right. And then if you look back on this left upper corner and you squint your eyes, you realize, okay, this actually does look like a dog head. And this is an ImageNet model, and in ImageNet, like a large part of the training set are dogs. So these models really love to hallucinate dogs all over. So whenever there is a kind of a possibility to see a dog, they are happy to see a dog and make the prediction like that. So this is kind of one way. This is kind of one way to try to use this fact that these representations are so nice and more human aligned to get some kind of insight into, into like why they make predictions the way they do, and kind of maybe kind of correct what kind of features like they depend on. And again, that's why I put counterfactual in quotes, because it's not really counterfactual, but this is kind of just, kind of the flavor that, that you would like to do. You would like to understand better, like kind of what would make you make this decision here, or what would make you make this decision here, and so on. That's kind of a useful way of interacting with the model. Okay, so yeah, I think it's really time for me to stop. So let's just pontificate. So I guess the one, one message that I hopefully conveyed enough is that never trust your model. Okay, so that our models are much less reliable than we might think. Okay, the fact that they get excellent accuracy on the test set, it doesn't really mean much. Okay, in particular, I also try to tell you is that like adversarial examples tend to arise from this existence of features in your data that are predictive, but they are just non-robust. They kind of are different type of features that we usually are used to, and that's the part of what they like of the beauty is that they are actually non-robust. And adversarial examples tend to correspond to flipping them. This, by the way, doesn't mean that this is the only way we can fool our models. It is possible, like some of the other explanations, they kind of also are true, but the adversarial examples that are usually appearing and the one that transfer correspond to these non-robust features. And again, and just like the adversarial robustness is not only about being robust to an adversary, it's really about understanding how our models learn. Like kind of the whole problem with adversarial robustness is just because the models tend to learn in a different way than we humans want them or expect them to do. And that's the real problem there. So I think what really I would like everyone thinking machine learning think about is kind of, I really don't like how kind of focused we are on one notion of what it means to succeed. It's just essentially, if I maximize my accuracy on the test set, I am good, and everything else doesn't matter anymore. Like, hopefully I made the case that clearly it matters a lot, and that, now leads to a question, okay, so what is the right notion of generalization? Like, how would we measure success of our model or our method, right? Again, I gave you robust generalization, which seems to be a bit better notion, but is it the right notion? I don't think so. Or at least, robust generalization is a very general notion because it always depends on the class of perturbations that you want to be robust to. So, is that what we should strive for? Maybe, but it's unclear to me, for sure. So that's something I don't have an answer, but I would like you to think about. And kind of, I really view adversarial robustness as kind of not as just a way of getting robust models, but just as kind of a framework for making our models better, in particular to do this feature engineering and kind of trying to regularize a bit in what way these complex deep learning models actually make predictions. So kind of you should think of adversary not as a bad guy who tries to undermine a model, but essentially think of a human critic that kind of tries to tell you, okay, in what way the way you make a decision is different to how human would make a decision. Okay, and I think that's a very useful tool. Okay, thank you.
So I collected a few questions from the discussion panel, and I hope you could answer some of them.
Sure.
Yeah, so the first question is, do you have results on how robust neural networks are different to standard neural networks? Are there properties, for example, minimum?
Yes.
And the values?
So answer is no, meaning like we didn't. That's an interesting question. Like the only thing that we definitely know that these models are different because the representations that they come up with are different. But honestly, beyond what I showed you, it's like there is no kind of, in particular in the context of what are the properties of the minimas, We don't know. Like that's a great question, by the way. It's just like kind of are the minimas different? I don't know. We kind of for now we are still in the level of what we learned and not how we learned. Like kind of we don't understand the mechanics of how the robust models look and how they differ from the non-robust models.
So the second question is about so how does susceptibility to evolve with training time?
Yeah. Yes, so that's a great question. That's something we are studying, but we don't know yet. So the question is exactly like, are the kind of, there seems to be this effect that the neural networks tend to pick on simpler patterns first, at least. But there is also connection to the learning the size of the to the learning rate. What is the learning rate? That there seems to be some development. So there is some interesting kind of phenomena about like that the models tend to first use the simple patterns and only later on they go to a bit less obvious patterns. So it's a great question. How does it look for robust and non-robust features? We don't know. Like that's something actually we really want to study, but we did not do that yet.
Okay, maybe the final question. Can we draw parallels between robust machine learning and active learning? We are essentially enriching the model by poorly classified data.
That's an interesting question. Like somehow it's unclear because like the goal of active learning is really like in some ways what of course you want to do, you want to minimize number of labels that you use, but of course to do so you exactly kind of figure out which of the currently unlabeled example will be most helpful for you. Kind of it's an interesting question. I don't know because like for now this is not where we focus on. Like kind of now we still are working in a fully supervised setup, and we don't think about what is the most useful, what are the most critical examples. We just use all of them and then use adversarial training on them. We do know, by the way, that using unsupervised kind of like essentially like using unlabeled data still helps with robustness. So essentially, like if you can do semi-supervised learning in a robust way, you get better results. But yeah, I think it's too early, at least for me, to say anything more than that.
So I guess we have run out of time, and if you have further questions, let's ask the speaker offline. Thank you for the speaker again for your time.
Yeah.